Chapter 3: Origins and Entropy. From Creation to Structure. When mathematics allows scientists to peer back to within a fraction of a second of what may well have been the beginning of the universe, the proximity to traditionally religious terrain suggests to some that there's a deep alliance or a deep connection or a deep conflict straining to be revealed. It's why I receive inquiries about my views on a creator almost as frequently as those asking about science. Indeed, questions often straddle the two. We will have ample time to consider such matters in later chapters, but here we will explore one point of contact, raised at the end of the previous chapter, essential to our larger story. If the second law of thermodynamics burdens the universe with a relentless increase in disorder, how can nature so readily produce exquisitely configured, highly ordered structures, from atoms and molecules, to stars and galaxies, to life and mind? If the universe began with an explosive bang, how could that fiery unfolding have given rise to all the organization, from the swirling arms of the Milky Way, to Earth's stunning landscapes, to the intricate connections and corrugated folds of the human brain, to the art, music, poetry, literature, and science such brains produce? One response, relied upon through the ages to address embryonic versions of such concerns, is that order is hewn from the chaos by a supreme intelligence. Human experience aligns with this anthropomorphically inspired turn. After all, much of the order we daily encounter in modern civilization is the handiwork of intelligence. But a proper exegesis of the second law renders an intelligent designer unnecessary. As surprising as it is remarkable, regions containing concentrated energy and order, stars being the archetypal example, are a natural consequence of the universe diligently towing the second law's line and becoming ever more disordered. Indeed, such pockets of order prove to be catalysts that facilitate the universe, over the long run, to reach its entropic potential. Along the way, and as part of this entropic progression, they also facilitate the emergence of life. To explore the dance between order and disorder playing out across cosmological history, we begin at the beginning. Sketching the Big Bang. In the mid-1920s, Jesuit priest Georges Lemaitre used Einstein's newly minted description of gravity, the general theory of relativity, to develop the radical idea of a cosmos that began with a bang and has been expanding ever since. Lemaitre was no armchair physicist. He received his doctorate from the Massachusetts Institute of Technology and was among the first scientists to apply the equations of general relativity to the cosmos as a whole. Einstein's intuition, which had successfully guided him through an exquisite decade of discoveries into the nature of space, time, and matter, was that objects in the universe have a beginning, middle, and an end, but the universe itself always was and would always be. When Lemaitre's analysis of Einstein's equations suggested otherwise, Einstein dismissed him out of hand, telling the young researcher, "Your calculations are correct but your physics is abominable." Einstein was emphasizing that you can be adept at manipulating equations and yet lack the good scientific taste to decide which of those mathematical manipulations reflect reality. A few years later, Einstein performed one of the most famous scientific turnabouts. Detailed observations by the astronomer Edwin Hubble, working at the Mount Wilson Observatory, revealed that distant galaxies are all on the move. They're all rushing away. And the pattern of their exodus, the farther the galaxy, the higher the speed, agreed with the mathematical output of general relativity's equations. With data now supporting Lemaitre's abominable physics, Einstein embraced wholeheartedly the conception of a universe that had a beginning. In the centuries since Lemaitre's innovative calculations, the cosmological theorizing he initiated, together with independent work by the Russian physicist Alexander Friedmann, has been substantially developed and a corpus of observational evidence from ground and spaceborne telescopes has been amassed. Here is the modern cosmological account that has emerged, some 14 billion years ago. The entire observable universe, all that we can see using the most powerful telescopes imaginable, was compressed into a stupendously hot, incredibly dense nugget, which then rapidly expanded. Cooling as it swelled, particles gradually slowed their frenzied motion and aggregated into clumps, which over time formed stars, planets, all manner of gaseous and rocky debris scattered across space, and us. In 2 sentences, that's the story. Let's refine it. Let's examine how, without intent or design, without forethought or judgment, without planning or deliberation, the cosmos yields meticulously ordered configurations of particles from atoms to stars to life. Let's understand how the emergence of such ordered structures squares with the second law's decree of relentlessly increasing disorder. Let's witness the entropic two-step now performed on the cosmological stage. To that end, we will need to understand various cosmological details more fully. First up, what drove the primordial nugget to start expanding in the first place? Or, in looser language, what ignited the Big Bang? Repulsive gravity. Antonyms abound because experience is full of opposites. Physics, too, has its share, order and disorder, matter and antimatter, positive and negative. But since the time of Newton, the force of gravity appeared to stand apart from this common pattern. Unlike the electromagnetic force, which can push or pull, gravity seemed to be solely an attractive force. According to Newton, gravity exerts a pull between objects, whether particles or planets, that draws them together, but never the reverse. Absent a principle that requires symmetry in all of nature's workings, most who thought deeply about gravity viewed its one-way character as an intrinsic quality that simply had to be accepted. Einstein changed this. According to the general theory of relativity, the gravitational force can be repulsive. Newton did not anticipate repulsive gravity, and neither you nor I have ever experienced it. But repulsive gravity does just what the name suggests. Instead of pulling inward, it pushes outward. According to Einstein's equations, big clumpy things like stars and planets exert the usual attractive version of gravity, but there are exotic situations in which the gravitational force can drive things apart. While the capacity of the gravitational force to be repulsive was known to Einstein, as well as a number of subsequent scientists who worked on the general theory of relativity, its most profound application took more than half a century to be discovered. As a young postdoctoral fellow contemplating the Big Bang, Alan Guth realized that repulsive gravity might address a confounding cosmic mystery. Observations reveal that space is expanding. Einstein's equations concur, but the equations remain mute on the question of what force, billions of years ago, set the expansion off and running. Guth's detailed mathematical analyses, culminating with a late-night calculational frenzy in December 1979, coaxed the equations to speak. Guth realized that if a region of space was filled with a particular kind of substance, something I like to call cosmic fuel, and if the energy contained in the cosmic fuel was spread evenly throughout the region, not clumped like a star or planet, then the resulting gravitational force would indeed be repulsive. More precisely, Guth's calculations revealed that if a tiny region, perhaps as small as a billionth of a billionth of a billionth of a meter across, was suffused with a certain type of energy field, called the inflaton field, with the missing I being an intentional if quirky naming convention, and if the energy was distributed uniformly, like steam whose density is the same throughout a sauna, the repulsive gravitational push would be so forceful that the speck of space would inflate explosively, almost instantaneously stretching to as large as the observable universe. if not far larger. Repulsive gravity would thus power a bang, and a big bang at that. 3. In the early 1980s, Soviet physicist Andrei Linde and the American duo Paul Steinhardt and Andreas Albrecht took Guth's hand off and ran with the concept, developing the first fully viable versions of inflationary cosmology. In the decades since, these early works have inspired thousands of pages of intricate mathematical calculations and a great many detailed computer simulations, filling journals worldwide with explanations and predictions based on the assumption of an inflationary past. Many of these predictions have now been confirmed by painstakingly precise astronomical measurements. While I won't lead you on a full tour of the observational case for inflationary cosmology, something amply covered in many articles and books, I'll describe one success that many physicists consider the most compelling of all. It is also the feature we will need for the next step in the cosmic unfolding, the formation of stars and galaxies. The afterglow. As the early universe rapidly stretched, its scorching heat spread over an ever-widening expanse, diminishing in intensity and cooling steadily. 4 Physicists as far back as the 1940s, long before the inflationary theory was developed, realized that the primordial heat, reduced by spatial expansion to a gentle glow, should still permeate the universe. Dubbed the afterglow of creation, or, in technical jargon, the cosmic microwave background radiation, this remarkable cosmological remnant was first detected in the 1960s by Bell Lab researchers Arno Penzias and Robert Wilson, whose advanced telecommunication antenna unwittingly tapped into a diffuse radiation permeating space, a mere 2.7 degrees above absolute zero. If you were around in the 1960s, you might have tapped into the radiation too. Part of the static on an old-style television tuned to a channel that had concluded its broadcast for the evening would have been due to this vestige of the Big Bang. Inflationary cosmology refines the prediction of an afterglow by taking into account quantum mechanics, the laws developed in the early decades of the 20th century to describe physical processes playing out in the micro-world. Since we're focused on the entire universe, something big, you might think the preoccupation of quantum physics with all things small would make it irrelevant. And if it weren't for inflationary cosmology, your intuition would be on the mark. But much as stretching a piece of spandex reveals the intricate pattern of its stitches, stretching space through a burst of inflationary expansion reveals quantum features usually cordoned off in the micro-world. In essence, inflationary expansion reaches into the micro-world and stretches quantum features clear across the sky. The quantum effect of most relevance is the very one that established an irrefutable break from the classical tradition, the quantum mechanical uncertainty principle. Discovered in 1927 by German physicist Werner Heisenberg, the uncertainty principle demonstrated that there are features of the world, like the position and the speed of a particle, that a classical physicist in the mold of Isaac Newton would adamantly claim can be specified with complete certainty, but that a quantum physicist realizes are burdened by a quantum fuzziness that makes them uncertain. It's as if the classical tradition viewed the world through pristine, polished spectacles that brought all physical features into perfectly sharp focus, while the spectacles donned by the quantum perspective are inherently foggy. In the large, everyday world of common experience, the quantum fog is too thin to impact our vision, so the classical and quantum perspectives are barely distinguishable. But the smaller you probe, the foggier the quantum lenses become and the fuzzier the view. The metaphor might suggest that all we need do is clean the quantum lenses. But the uncertainty principle established that no matter how fastidious we are and regardless of the advanced equipment we use, there will always be a minimal amount of fogginess that cannot be wiped away. In fact, my phrasing betrays the bias of human experience. It is only by comparison with the demonstrably incorrect classical view, The view we humans discovered first because it's both simpler and extraordinarily accurate on the scales accessible to human senses, that quantum reality seems hazy. It is actually the classical perspective that provides an approximate and hence precise view of the true quantum reality. I don't know why reality is governed by quantum laws. Nobody does. A century of experiments has confirmed a mountain of quantum mechanical predictions, and that's why scientists embrace the theory. Even so, for most of us quantum mechanics remains utterly foreign because its hallmark features emerge over distances so tiny that we just don't experience them in everyday life. If we did, common intuition would be shaped directly by quantum processes and quantum physics would be second nature. Much as you know the implications of Newtonian physics in your bones, you can quickly grab a falling glass, instantly intuiting its Newtonian trajectory. You'd know quantum physics in your bones too. But lacking such quantum intuition, we rely on experiment and mathematics to mold our understanding by portraying aspects of reality we can't directly experience. The most widely discussed example, already mentioned, concerns the behavior of particles, where we learn to modify the sharp trajectories inherent in classical physics by overlaying incessant jittery motion from quantum uncertainty. As a particle transits from here to there, a classical physicist might draw its trajectory with a pointed quill, while a quantum physicist would run her finger along the wet ink, smearing out the path. 5 But quantum mechanics has relevance far beyond the motion of individual particles. And for cosmology, the quantum uncertainty principle has a decisive influence on the inflaton field that fuels the rapid expansion of space. Although I described the inflaton's value as being uniform, taking on the same value at all locations within the inflating patch of space, quantum uncertainty fuzzes this out. Uncertainty overlays quantum jitters on the classical uniformity, resulting in the field's value, and hence its energy, being a tiny bit higher here and a tiny bit lower there. When inflationary expansion rapidly stretches these minute quantum energy variations, they spread across space, making the temperature a touch hotter over here and a touch cooler over there. Not by much. Mathematical analyses, first carried out by physicists in the 1980s, showed that the temperatures of hot and cold spots would differ by as little as 1 part in 100,000. But the mathematical analyses also suggested that the tiny temperature variations would be visible if you knew how to look for them. The calculations revealed that the stretched-out quantum jitters result in a distinct pattern of temperature variations across space, a cosmological fingerprint available for astronomical forensics. Indeed, since the early 1990s, a sequence of telescopes deployed above the distortions caused by Earth's atmosphere have confirmed the predicted pattern of temperature variations with ever greater precision. Take a moment to let this sink in. Physicists describe the earliest moments of the universe using Einstein's equations, updated to include Guth's hypothetical energy field filling space, subject to the quantum uncertainty we learned from Heisenberg. Mathematical analyses of the inflationary burst then reveal that it should have left an indelible imprint, a fossil of creation in the form of a specific pattern of minute temperature variations across the night sky. Sophisticated space-based thermometers built nearly 14 billion years later by a species just coming of scientific age here in the Milky Way have now detected precisely that pattern. It is a spectacular success, demonstrating once again the uncanny capacity of mathematics to encapsulate nature's patterns. But it would be too strong to conclude that the observations prove that a burst of inflationary expansion happened. When focusing on cosmological events that took place billions of years ago, at an energy scale likely millions of billions of times what we can probe in the laboratory, The best we can do is piece together observations and calculations to build confidence in our explanations. If an inflationary burst were the only way to understand the cosmological data, then our confidence would head closer to certainty. But over the years, imaginative scientists have developed alternative approaches. We will encounter one of these in Chapter 10. All told, my view, shared by many researchers, is that while we need to be open to novel ideas that challenge dominant perspectives, the case for inflationary cosmology developed over the past 40 years is formidable. 6 And so as our journey heads onward, we will, for the most part, follow the inflationary trail. With that assessment, let's now consider how an inflationary beginning interfaces with the second law's drive toward greater disorder, the Big Bang and the second law. Notwithstanding centuries of scientific progress, we are no closer to answering the question raised by Gottfried Leibniz, why is there something rather than nothing, than we were when the German philosopher first expressed this lean distillation of the mystery of existence. Not that people haven't proposed creative ideas and provocative theories, but in asking a question of ultimate origin, we are seeking an answer that requires no antecedent, an answer that does not shift the question one step further back, an answer that is immune to the follow-on questions: why were things this way instead of that? Or why these laws instead of those? No explanation yet proposed has achieved this or even come close. The inflationary framework surely hasn't. Inflation requires a list of ingredients that includes space, time, the cosmic fuel driving the expansion, the inflaton field, as well as the whole technical apparatus of quantum mechanics and general relativity, which themselves rest upon mathematics from multivariable calculus and linear algebra to differential geometry. There is no known principle that singles out these particular physical laws, articulated using these particular mathematical constructs, as the inevitable starting point for explaining the universe. Instead, we physicists use observation and experiment, together with a hard-to-describe intuitive mathematical sensibility, to guide us toward particular physical laws. We then analyze the laws mathematically to determine which environmental conditions in the earliest moments of the universe, if any, would have sparked the rapid expansion of space. Upon finding, happily, that there are such conditions, we postulate that they held near the Big Bang, and we use the equations to determine what subsequently would have happened. This is the best we can currently do, and it's nothing to sneeze at. The fact that we can use mathematics to describe what we think took place nearly 14 billion years ago, and from that successfully predict what powerful telescopes should now see, well, it is breathtaking. Sure, profound questions abound, like what or who created space and time, and what or who imposed the guiding grip of mathematics, and what or who is responsible for there being anything at all. But even with all that left unanswered, we've gained powerful insight into the cosmic unfolding. My intent here is to use that insight to grasp how a universe with ever-increasing entropy, destined for ever greater disorder, creates a wealth of order along the way. With that as our target, let's start with the most basic observation, alluded to in the previous chapter. If entropy has been steadily increasing since the Big Bang, then the entropy back at the Bang must have been much lower than it is today. 7. What are we to make of this? Well, by now you've grown accustomed to shrugging your shoulders when encountering a high entropy configuration, be it coins arranged in a random mixture of heads and tails, steam that uniformly permeates your bathroom, or aromas spread throughout your house. High entropy configurations are expected, common, run-of-the-mill. But when encountering a low entropy configuration, you realize that your reaction should be different. A low entropy configuration is special. It is unusual. It calls out for an explanation for how such an ordered state of affairs came to be. When applied to the early universe, This reasoning has generated its share of scientific and philosophical hand-wringing. By what force or process did the early universe acquire low entropy? 100 pennies with all heads has low entropy and yet admits an immediate explanation. Instead of dumping the coins on the table, someone carefully arranged them. But what or who arranged the special low-entropy configuration of the early universe? Without a complete theory of cosmic origins, science can't provide an answer. In fact, although it's a question that has kept me up for many a night, literally, science can't yet determine whether it's an issue worthy of any angst at all. Lacking an understanding of why there is something rather than nothing is tantamount to lacking the means to judge how exotic or ordinary that something actually is. To assess whether the detailed conditions of the early universe call for a shrug or a wide-eyed double-take requires delineating the process by which those conditions were set. One scenario that cosmologists have considered imagines that the early universe was a frenzied and chaotic environment, and as a result the value of the inflaton field across space would have fluctuated wildly, somewhat like the surface of boiling water. To generate repulsive gravity and set off the bang, we need a small region of space in which the inflaton's value is uniform, or very nearly so, taking into account quantum jitters. But finding such a uniform region amid the chaotic undulations would be like boiling a vat of water and finding a region on its agitated surface that had suddenly flattened. You have never seen that happen. Not because it's impossible but because it's extraordinarily unlikely for a region of the vat's randomly bubbling water to pass through the same height at the same moment, yielding a flat, orderly, uniform, low-entropy configuration would require an astounding coincidence. Similarly, for the wildly undulating inflaton field to have acquired a uniform value within a small region of space, thus igniting inflationary expansion, would have required an astounding coincidence too. And without an explanation for how this special, orderly, low-entropy, uniform configuration came to be, physicists are deeply uneasy. 8. Seeking relief from the discomfort, some researchers rely on a simple observation: if you wait long enough even the most unlikely of things will happen. Shake 100 pennies enough times and eventually they will land all heads. You'd be wise not to hold your breath waiting for this outcome, but it will happen. Similarly, we can argue that in a chaotic environment in which the inflaton's value fluctuates wildly, sooner or later, by sheer chance, there'll be a tiny region in which the random variations that drive the field's value up here or down there will align, resulting in the field having the same value throughout. This requires a statistical fluke, resulting in greater order and hence lower entropy. But on occasion it will happen. Not often. But according to this perspective, don't sweat it. Since all of these machinations would have taken place during a period of prehistory, before the rapid expansion of space we call the Big Bang, there was no one hanging around, arms crossed and shoe tapping, waiting for inflationary expansion to ignite. So let the inflationary pressure run as long as it takes. It is only when the statistical fluke of a uniform inflaton patch happens to happen that things finally change, the Big Bang is sparked, space inflates, and the cosmological performance begins. While none of this addresses the most fundamental questions of origin, the origin of space, or time, or fields, or mathematics, and so on, it shows how a chaotic environment can produce the special, ordered, low-entropy conditions inflation requires. When a tiny speck of space finally makes the statistically unlikely leap to low entropy, repulsive gravity jumps into action and propels it into a rapidly expanding universe, the Big Bang. This is not the only proposal for how inflationary expansion may have gotten off the ground. André Linde, one of inflationary cosmology's pioneers, has quipped that for every 3 researchers there are at least 9 opinions on the matter. 9 So we must leave to future research, theoretical and observational, a more definitive answer for how a small region of space became uniformly filled with an inflaton field, thus setting off a burst of spatial expansion. For now, we will simply assume that one way or another, the early universe transitioned into this low entropy, highly ordered configuration, sparking the bang and allowing us to declare that the rest is history. Starting from this trailhead, we now set off on our trek, exploring how orderly structures like stars and galaxies form within a universe hurtling toward an ever more disordered future. The origin of matter and the birth of stars. Within a billionth of a billionth of a billionth of a second after the Big Bang, repulsive gravity stretched a tiny region of space enormously, perhaps far larger than the most distant reaches accessible to the most advanced telescopes possible. 10 Space remained filled with the inflaton field, but within another tiny fraction of a second that changed too. Like the energy in the surface of an expanding soap bubble, the energy in an expanding inflaton-filled region of space is precarious. It's unstable. Much as the soap bubble will eventually pop, transforming its energy into a mist of soapy water droplets, the inflaton field eventually popped too. It disintegrated, transforming its energy into a mist of particles. We don't know the precise identity of these particles, but we can say with confidence that they were not the ordinary constituents of matter you learned about in junior high school. Yet, with the passage of just a few more minutes, a cascade of rapid particle reactions took place all across space, heavy particles disintegrating into sprays of lighter ones, particles with strong affinities joining together into tight conglomerates, transforming the primordial bath into a population of protons, neutrons, and electrons, the stuff of familiar matter, and, likely too, a supply of other more exotic particles, such as dark matter, attested to by a long history of astronomical observations. 11. Within a short time after the bang, the universe was thus filled with a hot, nearly uniform mist of particles, some familiar, others less so, wafting through a swelling spatial expanse. I've qualified uniform with nearly because quantum jitters of the inflaton field not only yield temperature variations in the Big Bang's afterglow, but also ensure that when the inflaton disintegrates, the density of the resulting particles will vary slightly across space, being a touch higher here, a touch lower there, and so on. These variations are crucial for what happens next. The all-important drive toward clumpy things like stars and galaxies. A region that's slightly denser than its neighbors exerts a slightly greater gravitational pull and so sucks in a slightly greater contingent of the surrounding particles. The region thus becomes denser still, and so exerts an even greater gravitational pull, sucking in yet more material. It's a gravitationally driven snowball effect that yields larger and larger clumps of matter. Wait long enough, on the order of hundreds of millions of years, and the gravitational snowballing yields particle agglomerations so massive, so compressed, and so hot that they ignite nuclear processes, giving birth to stars. Quantum uncertainty, magnified by inflationary stretching and concentrated by gravitational snowballing, results in the points of light dotting the night sky. The question, then, is this: how does the star-forming process, in which gravity coaxes a disordered, nearly uniform bath of particles to form ordered astrophysical structures, square with the second law's decree of increasing disorder? The answer requires that we examine, with a little more care, the pathways toward higher entropy. Hurdles on the path toward disorder. As bread bakes in your oven, the particles released spread outward, occupying an increasingly large volume, and so their entropy grows. But if you are in a distant bedroom, you won't immediately enjoy the bread's freshly baked aroma. It takes time for the aroma to spread through your house. You have to wait for the aroma molecules to migrate outward and occupy the higher entropy arrangements that are available. This is typical. Physical systems generally can't jump directly to the maximum entropy configuration. Instead, as the system's particles meander randomly, entropy gradually increases toward the maximum possible. Along the pathway toward higher entropy, there can also be hurdles that impede progress. Seal the oven or close the kitchen door and you make it harder for the aroma to spread, thus slowing the rise in entropy. Such hurdles are due to human intervention. But there are other situations in which entropic hurdles arise from the laws governing physical interactions themselves. An example with which I'm intimately familiar from a childhood incident also involves an oven. One day during 4th grade I came home from school and decided to heat some leftover pizza I found in the refrigerator. I turned the oven to 400 degrees, slid the pizza onto the middle rack, and waited. After about 10 minutes I checked on its progress and was surprised that the pizza was just as cold as when I unwrapped it. It then dawned on me that although I'd turned on the gas, I'd forgotten to light the oven. Our modest oven, typical of the day, did not have a built-in pilot light, so each use required it to be lit. Following a procedure I'd witnessed my parents undertake hundreds of times, I leaned into the oven and struck a match, intending to poke it into the oven's small pilot hole. By this point substantial gas had accumulated in the oven's interior, and so when I lit the match it exploded. A wall of flames raced toward me. I tightly closed my eyes as the fire blew by, singeing off my eyebrows, eyelashes, and leaving my face and ears with 2nd and 3rd degree burns. The immediate life lesson, emphasized by my parents and reinforced by the months of painful healing, focused on proper use of kitchen appliances. I eventually got back in the saddle and now do most of the cooking, although I do experience momentary unease when my kids, preparing their own meals, turn on the oven. But the larger scientific point is that there can be roadblocks along the journey to higher entropy that can be surmounted only with the help of a catalyst. Here's what I mean. Natural gas, which is mostly methane, a union of carbon and hydrogen, can peacefully coexist with the oxygen in air. The molecules of each gas can uneventfully commingle. However, as the molecules spread and intersperse, a distinct and far higher entropy configuration beckons. But that configuration cannot be reached by simply allowing molecules to continue fanning out. The higher entropy configuration requires a chemical reaction. Don't sweat the details, but let me briefly spell it out. One molecule of natural gas can combine with 2 molecules of oxygen, resulting in 1 molecule of carbon dioxide, 2 of water, and, of prime importance, a burst of energy. At the level of molecules, this is what it means for natural gas to burn. The chemical reaction releases energy pent up in the tight bonds holding the gas molecules together, kind of like what happens when a collection of taut rubber bands snap. In the case of my oven escapade, that searingly energetic burst, highly agitated and fast-moving molecules, scorched my face. All of which tells us that by releasing energy stored in orderly chemical bonds and transforming it into the chaotic motion of rapidly moving molecules, such chemical reactions yield a sharp increase in entropy. Though the details are specific to one child's regrettable mishap, the episode demonstrates a widely applicable physical principle. There can be speed bumps in the entropic road. Left on their own, natural gas and oxygen won't combine, they won't burn, and they won't reach the higher entropy configuration that's available. These chemical constituents are able to clear the entropic hurdle only with the help of a catalyst that can jumpstart the reaction. For me, The catalyst was a burning match. The little flame struck by my fourth-grade self set off a domino effect. The flame's energy broke the bonds holding some of the natural gas molecules together, allowing newly freed carbon and hydrogen atoms to combine with ambient atoms of oxygen, which released additional energy that severed more natural gas bonds, driving the process onward and onward. The explosion was the cascade of energy generated by the rapid rearranging of chemical bonds. Note that chemical bonds rely on the electromagnetic force. Positively charged protons attract negatively charged electrons, unlike electric charges attract, clasping atomic constituents into molecular unions, which means that the entropic leap from the calm intermingling of gas molecules to the explosive burning generated by the breaking and forging of chemical bonds is driven by the electromagnetic force. Such is the case for many of the entropy-increasing processes we experience in everyday life, although less familiar here on Earth, in episodes that repeatedly play out in the cosmos. The evolution toward higher entropy is frequently driven by nature's other forces, the gravitational force and the nuclear forces. The strong nuclear force holds atomic nuclei together, while the weak nuclear force generates radioactive decay, and much as we've now seen in the case of the electromagnetic force, the path toward higher entropy blazed by gravity and the nuclear forces need not be smooth either. There can be hurdles, and there often are. The way the universe surmounts these hurdles, the cosmic analog of my striking a match, is a subtle business. But it's a business we should all care about deeply. Among the transient structures that form as gravity and the nuclear forces guide the universe toward higher entropy are stars and planets, and here on Earth, life. For all their majesty, these orderly arrangements are nature's workhorses, harnessing gravity and the nuclear forces to drive the cosmos toward realizing its entropy potential. Let's focus first on gravity. Gravity, order, and the second law. Gravity is the weakest of nature's forces, a fact made evident by the simplest demonstration. Pick up a coin. The muscles in your arm beat out the gravitational pull of the entire Earth. Whether you consider yourself soft or strapping, victory over the gravitational pull of a planet highlights gravity's intrinsic weakness. The only reason we're even aware of gravity is that it's a cumulative force. Every bit of the Earth pulls on every bit of a coin, and on every bit of this book, and on every bit of you, and since there's a whole lot of Earth, these pulls add up to downward forces we can feel. But the gravitational attraction between two smaller things, like two electrons, is a million billion times weaker than their electromagnetic repulsion. The intrinsic weakness of gravity is why we didn't even mention it during our earlier exploration of entropy. Were we to include the effects of gravity in everyday situations like the spreading of steam in your bathroom or the drifting of aromas through your house, our discussion of entropy would hardly change. Sure, gravity gently tugs the molecules downward, causing the steam's density to be slightly larger closer to the bathroom floor, but the effect is so small that for a qualitative understanding it just doesn't matter. However, if we shift our attention from the everyday and consider astronomical processes involving a great deal more matter, we encounter a profoundly important interplay between entropy and the gravitational force. Admittedly, the ideas I'll now explain are somewhat challenging, so feel free to skip to the next section for a summary if at any point the discussion gets too thick for your taste. But the payoff for sticking with me is worthwhile. An understanding of how gravity spontaneously sculpts order from an ever more disordered cosmos. Imagine a cosmic version of the bread baking scenario. Instead of your house, imagine an enormous box, much larger than the sun, floating in otherwise empty space. And instead of aromas seeping from your oven, imagine that in the middle of the box we start with a ball of gas. To be definite, imagine it's hydrogen, the simplest element on the periodic table, whose molecules are oozing outward. From our experience with the bread's aroma drifting throughout your house, we expect that the gas will evolve toward higher entropy via the molecules dispersing until they uniformly fill the box. But now let's change things a bit. Unlike the case of baking bread, let's add so many molecules into the ball of gas that gravity does matter. The gravitational pull experienced by any given molecule, due to the combined gravitational pull exerted by each of the gargantuan number of other gas molecules, significantly affects the molecule's motion. How does this impact our conclusion? Well, put yourself in the shoes of a gas molecule leading the outward migration. As you stream away from the central cluster, you feel a gravitational pull exerted by all the other molecules tugging you back. That force slows you down. Slower speed means lower temperature. And so as the gas cloud increases its overall volume by expanding outward, the temperature toward the frontier decreases. Hold that in mind. And now jump with me to the perspective of a molecule located nearer to the bulk of the cloud. Being closer, you feel a much stronger gravitational pull compared to your previous experience on a distant frontier. In fact, with enough molecules, the combined gravitational pull will be sufficiently strong to prevent you from migrating outward at all. Instead, you will be pulled inward. You'll thus fall toward the center of the gas cluster, picking up speed as you go. Faster speed means higher temperature, and so as gravity causes the core of the gas cloud to shrink inward, decreasing its volume, its temperature goes up. Compared with our expectation from baking bread, that the gas would, over time, become evenly distributed throughout the box and attain a uniform temperature, we see that when gravity matters the unfolding is completely different. Gravity results in some molecules being pulled into a hotter, denser core, while others drift outward into a cooler, more diffuse shell that surrounds it. Modest though these observations may appear, we've now uncovered one of the most influential guiding hands of order in the universe. Let me elaborate. You've never clutched hold of your morning coffee and found it hotter than when you poured it. That's because heat flows only from higher temperature to lower temperature, and so your hot coffee transfers some of its heat to the cooler environment, causing the coffee's temperature to decrease. 12 For our large cloud of gas, heat also flows from the hot central core to the cooler surrounding shell. Now, I can't fault you for thinking that this flow of heat will cool the core and warm the shell, bringing their temperatures closer together, much as heat transferred from your coffee to the air brings your hot mug closer to room temperature. But, and this is remarkable and remarkably important, when gravity is directing the show, the conclusion is reversed. As heat flows out from the core gets hotter and the shell gets cooler. This is surely counterintuitive, but understanding it is just a matter of connecting dots we've already marked. As the surrounding shell absorbs heat from the core, the additional energy drives the cloud to swell even further. The outward moving molecules, once again, strain against the inward pull of gravity, and hence are slowed even further. 13 The net effect is that the temperature of the expanding shell goes down, not up. Conversely, as the core relinquishes heat, the decrease in energy causes it to contract even further. The inward moving molecules, flowing in the same direction as the inward pull of gravity, pick up speed as they fall, and so the temperature of the contracting core goes up, not down. If your coffee behaved this way, you'd be well advised to drink it quickly. The longer you'd wait, the more heat it would relinquish to the surrounding air and the hotter it would become. For coffee, that's absurd. But for a gas cloud large enough for gravity to play a dominant role, this is what happens. Dwell on this conclusion for a moment and you'll realize that we've encountered a self-amplifying process. Much like what happens with credit card debt, the more you owe, the more interest you're assessed and the greater your debt becomes, driving the cycle to spiral. For a gas cloud, as the core shrinks and its temperature rises, it will relinquish yet more heat to the cooler surroundings, causing the core to shrink yet further and its temperature to rise yet higher. At the same time, the heat absorbed by the shell causes it to expand yet further and its temperature to fall yet lower. The ever-widening gap in temperature between the core and the shell causes heat to flow yet more vigorously and drives the cycle to spiral onward. Barring intervention or change of circumstance, such self-amplifying cycles continue unabated. For mounting credit card debt, you intervene by sending a payment or declaring bankruptcy. For the compressed core that's getting ever hotter, nature intervenes with a new physical process, nuclear fusion. When a collection of atoms gets sufficiently hot and dense, they slam together with such force that they can meld more deeply than they do in chemical processes like the burning of natural gas. Whereas chemical burning is a reaction that involves the electrons that surround atoms, nuclear fusion is a reaction that joins nuclei at the center of atoms. Through such deep melding, nuclear fusion generates copious quantities of energy manifested as rapidly moving particles. And it is such rapid thermal motion that generates an outward pressure capable of balancing the inward force of gravity. Nuclear fusion in the core thus halts the contraction. The result is a concentrated, stable, and sustained source of heat and light. A star is born. To appreciate how the formation process tallies on the entropy scoreboard, let's add up the contributions. Both the core of the gas cloud, which becomes the star, as well as the shell of the gas that surrounds it, are subject to two competing entropic effects. For the core, temperature goes up, acting to increase entropy, and volume goes down, acting to decrease entropy. Only detailed calculation 14 can determine the winner, with the result being that the decrease exceeds the increase, so the core's net entropy goes down. The formation of large gravitational clumps, like stars, is indeed a move toward greater order. For the surrounding shell, volume goes up, acting to increase entropy, and temperature goes down, acting to decrease entropy. Again, detailed calculation is required to determine the winner, with the result being that the increase exceeds the decrease, so the shell's net entropy goes up. Just as important, the calculations establish that the entropy increase of the shell exceeds the entropy decrease of the core, ensuring that the entire process results in an overall increase of entropy, earning a well-deserved nod of approval from the second law. The chain of events, highly idealized and simplified to be sure, shows how a star, a pocket of low entropy, a pocket of order, can be produced spontaneously even though no engineer directs the action and even though the second law of thermodynamics, with its dictum that total entropy increases, remains in full force. Compared with a steam engine, the cosmic setting is more exotic. But what we've found is another instance of the entropic two-step. Much as a steam engine and its surrounding environment engage in a thermodynamic dance, the steam engine releases waste heat, causing its entropy to decrease, while the environment soaks up the heat, causing its entropy to increase. A gas cloud that's large enough for gravity to matter engages in an analogous podida. As the core of such a gas cloud contracts under the pull of gravity, its entropy decreases, but in the process it releases heat that causes the entropy of the surroundings to increase. A local region of order is created within an environment that undergoes a more than compensating surge in disorder. The new feature of the gravitational version of the entropic two-step is that it's self-sustaining. As the gas cloud contracts and emits heat, its temperature rises, causing yet more heat to flow outward and driving the two-step to continue stepping. By contrast, when the steam engine performs work and emits heat, its temperature drops. Without burning more fuel to heat the steam back up, the engine peters out. That's why the steam engine requires a clever intelligence to design, build, and power it, while the region of order created by a contracting cloud of gas, a star, is sculpted and powered by the mindless force of gravity. Fusion, order, And the second law. Let's take stock. When gravity's influence is minimal, the second law drives a system toward homogeneity. Things spread out, energy diffuses, entropy increases. And if that's all there was, the story of the universe, beginning to end, would be bland. But when there's enough matter for gravity's influence to be significant, the second law undertakes a rapid U-turn, and drives the system away from homogeneity. Matter clumps here and spreads out there. Energy concentrates here and diffuses there. Entropy decreases here and increases there. The manner in which the second law's directive is carried out thus depends sensitively on the force of gravity. When there's enough gravity, enough sufficiently concentrated stuff, ordered structures can form. With that, the story of the unfolding universe becomes far richer. As described, the starring role in this process is played by the force of gravity. By comparison, the nuclear force, responsible for fusion, seems decidedly secondary. Its job appears limited to an intervention. Fusion results in the outward pressure that halts the inward collapse driven by gravity. Indeed, an offhand summary scientists commonly rehearse is to say that gravity is the ultimate source of all structure in the cosmos, offering nary a nod to the role of the nuclear force. But a more generous appraisal is that there's an equitable partnership between gravity and the nuclear force as they work in tandem to advance the second law's narrative. The point is that the nuclear force dances the entropic two-step too. When atomic nuclei fuse, as in the Sun, where hydrogen nuclei fuse into helium billions and billions of times each second, the result is a more complex, more intricately organized, lower entropy atomic cluster. In the process, some of the mass of the original nuclei is converted into energy, as prescribed by E=mc², mostly in the form of a burst of photons that heats the star's interior and powers the release of light from the star's surface. And it is through such fiery starlight, which is itself a torrent of outward streaming photons, that the star transfers copious quantities of entropy to the environment. Indeed, much as we found with the steam engine, and with the contracting gas cloud, the increase in environmental entropy more than compensates for the decrease in entropy from fusing nuclei, ensuring that the net entropy goes up and the integrity of the second law is once again secured. Just as natural gas and oxygen need a catalyst, such as my striking a match, to initiate chemical burning, atomic nuclei need a catalyst to spark nuclear fusion. For stars, that catalyst is none other than the force of gravity, crushing matter in the core until it becomes sufficiently hot and dense for fusion to ignite. Once fusion begins, it can power a star for billions of years, relentlessly synthesizing complex atomic nuclei as it extracts an otherwise inaccessible trove of entropy that it sprays outward through heat and light. And as we will discuss in the next chapter, these products, complex atoms and a steady bath of streaming light, are essential for the formation of even richer and more intricate structures, including you and me. Thus, although gravity is the vital force in the formation of a star and in maintaining a stable stellar environment, for billions of years it's the nuclear force that's on the front line, spearheading the entropic charge. From this perspective, gravity's role shifts from leading protagonist to indispensable partner in a long duet. The upshot, anthropomorphized, is that the universe cleverly leverages the gravitational and nuclear forces to wrest a cache of untapped entropy that's locked up inside of its material constituents. Without gravity, particles that are uniformly dispersed, like an aroma that has filled your house, have attained the highest entropy available. But with gravity, particles that are squeezed into massive and dense balls supported by nuclear fusion drive the entropy tally yet higher. Catalyzed by gravity and executed by the nuclear force, this version of the entropic two-step is danced by matter clear across the universe. It's a process that has dominated the cosmic choreography since shortly after the Big Bang, resulting in vast numbers of stars, orderly astronomical structures whose heat and light, in at least one instance, enabled the emergence of life. That development, as we will explore in the next chapter, involves a counterpart to entropy, evolution, that is capable of shaping the most exquisitely complex structures in the universe. A note about the author: Brain Greene is a professor of physics and mathematics at Columbia University and is renowned for a number of groundbreaking discoveries in string theory. He is the author of the New York Times best-selling books The Elegant Universe, The Fabric of the Cosmos, and The Hidden Reality. Greene hosted 2 award-winning Nova miniseries based on his books and is also a co-founder of the World Science Festival. With his wife and children, he lives in Andes, New York, and in New York City.